Okay, thanks. Yeah, I'm quite familiar with you, your ID and your name. Your name, some of you, yeah, I'm quite familiar. Yeah, really, I'm sorry that we can't meet in person. I know some of you just really have difficulty to connect to the network. So you're very good. But trust me, really, knowledge can change your life. Okay. I help you have a better life. Okay. So I would like to play Dujian irrigation dam to you again, okay? Because it's really good. I'm proud of this because I'm Sichuan. Yeah, me. I mean, I'm Sichuan local. Okay, I'm Sichuan person, and this irrigation dam help our Sichuan province just to prevent flood, prevent drought, and for 2,000 years, and it still work. Okay, very good one.
都江堰，都江堰。
Sorry, no, that's wrong.
都江堰，都江堰。Around 2,200 years ago, a governor of Sichuan found that the floods happened frequently in the rainy season, and water storage was short during the dry season. Therefore, based on the geographic features of the Minjiang River and without doing any damage to the natural environment, he built a special structure dam. The dam is known as Dujiangyan. Dujiangyan functions to direct water and divert floods and sand. Thanks to the dam, the region will no longer be plagued by flooding during the rainy season, and water supply will be sufficient in the dry season. Dujiangyan has functioned for more than 2,200 years. Even the earthquake with a magnitude of 7.8 on the Richter scale in 2008, which happened near the dam, didn't destroy it. Dujiangyan reflects the idea that the land, water, and people can live in harmony.
Hello, China. For this, you got serious videos. You can watch this. You can know more about China. Okay. And Zhejiang irrigation dam is really famous for its. It got fish moss type dividing dike. The fish moss you will see in the photo of the Zhejiang. Let's see here. You got a fish mouth. Okay, you can just go to see it by yourself. Okay, so you say no matter you like fluid mechanics, no matter you like hydraulics or not, it is here. You hydraulics really help you. Okay, and you say it's a day full of fluid mechanics, full of hydraulics, just like you wake up in a winter morning and the room is comfort warm because the radiator heat Okay. Wash your face and the water just first pass through a flow meter outside your house and travel inside the pipes before coming to the faucet. Okay, the pipe system. It's you, civil engineer, who will be in charge of the design of the pipe system. Okay. And here, this is what I did. Okay, what I'm doing, the fluid mechanics of human body, we call cardiovascular system or hemodynamics. Okay, so I work with clinicians. I work with doctors. Okay, we got a lot of application of fluid mechanics or hydraulics, okay, for the airspace. Okay, so for the even also for the weather forecasting, also we need knowledge of hydraulics. So hydraulics is quite important, right? And also is interesting. And so let's start it now. Starting of hydraulics, okay? So the introduction, okay? Properties of fluids, okay? Need to share this. Okay, before we just start the learning of hydraulics, I would like to introduce the important units and dimensions. I just would like to tell you the units and dimensions you use are quite important. Why? Because we have different, right, in theoretic mechanics, we have talked about this already. We have international dimension unit system. Also, we have the British unit system. Okay, and most of the countries use international unit system, but still there are some countries still use British unit system. Okay. Before we know about the units, we need to know the dimensions. We have primary dimensions. We have the first quantities. The primary dimensions also called the primary quantities to describe the physical property of the solids, of the fluids, okay? First, length, okay? And then time, and then mass. Sometimes we don't use force. We don't use mass, we use force. Anyhow, we also have temperature for thermodynamics, but for us, for this course or for thermodynamic mechanics, we only have three dimensions being the primary quantity or the primary dimension, length, time, mass. You can check that. Will find out that any physical quantities is they are actually a combination of the primary dimensions. Just like the velocity. Velocity is a combination of the length and time, right? Just like the density, you got the mass, you got the length, okay, the dimension, right? So any physical quantity or any second quantities, they are just the combination of the primary dimensions. And here, just like we say, any physical quantity is actually the combination of the length to the power of alpha, time to the power of beta, m to the power to gamma. Okay, if the power of the length is equal to 0, the power of the time also equal to 0, and the power of the mass is also equal to 0. We just say they are dimensionless variables, and later on you will just like a Reynolds number, they are dimensionless. Just like the drag coefficient, they are dimensionless. That means they have no units. Okay, they are no, there is no dimension. But sometimes we will just only have the dimension of length. So they are called geometrical parameters, just like area, just like volumes. They are the geometrical parameters. And sometimes we only have the dimension of we have the dimension of the length and time. We call they are kinematical parameters, just like velocity and acceleration. Okay, but some parameters, some variables belong to dynamic parameters. They not only have the dimension of length, also evolved with time and mass. Okay, so but anyhow, you can check out all the quantities we have learned in thermometric mechanics and in hydraulics. You found that any variable, any quantities are the combination of the three primary dimensions. Just now we said that we have the length, time, and mass as the primary dimensions, or the length, time, force are the primary dimensions. Why? Why just force or mass? Think about the Newton's second law. Newton's second law, we say force on the resultant force, the external resultant force on the rigid body equal to the mass times the acceleration, right? And you say the force is actually equal to the mass times length times the dimension, dimension and times, right? So force and mass, they are not independent with each other. Okay, so you can choose the length, time, mass, or you can choose the length, time, and force. And this part we will have one chapter to describe this. But before we start the course, you need to know that all the variables actually are a combination of the three primary dimensions. And for any equations, for any relationship A equal to B, it's very important that the dimension of the left-hand side A equal to the dimension of the left-hand side B, or we say the units of part A should equal to the units of part B. We say they should be dimensional homogeneity. Okay, they should be dimensional homogeneous. Okay, so for any equations you memorize, sometimes you can get wrong, so you can check out whether they have the same design, same dimensions. I mean, left and right hand side. Okay, it's very, very important. So we have different unit system, British unit system and international system. For the length, we have meter, we have centimeter, we have foot, and for the time, just they both equal to second. But for the mass, we got pound, we got kilogram, and sure, definitely. But also for temperature, we have different temperature depression. Okay, so it's very important for the units. Okay, the units are quite important. If you should consist with one unit system, just like for some Chinese students, they told me that because the textbook they use is the one I just recommend to you, fundamental of fluid mechanics. The system in that textbook is actually a British unit system, and so for them, they told me they just transfer all the units to the international unit system because they are quite familiar with the international unit system. So they transfer them to the international unit system directly every time. Okay, so you will have the formulas to transfer them. You don't need to memorize them. Okay, why it's important? We just give you an example. Just for NASA, you know NASA, right? NASA for USA, right? Just like the metric mishap caused the losses. It's thousand. Okay, it's 125 million USA dollars. Okay, so just because the technicians use different the unit system, so just keep in mind you just only adopt one unit system. Okay. So we have talked about what is hydraulics. I don't want to redo that again. And so what is a fluid? Just now we try to explain what's fluid in just to tell them what's fluid, just like to describe what's fluid. We know that liquid and gas both belong to fluid, and just like water and the air, they are fluid. And but still, we just don't know the exact definition what's fluid. And also, just maybe if you just tell the difference between solid and fluid, maybe you say solid, they are hard, they just are not easy to deform, right? Solid are not easy to deform. They are not easy. They can be cut into small pieces, right? They can be cut into small groups. Okay, just like steel is not easy to cut steel into pieces, but still, if you got harsh life, you can still do that, right? That's for solid, but for the fluid, we just think it's soft and they can be cut into small pieces. Okay, in China, for Chinese, we always like to use metaphor to steel to be man and water to be woman. Okay, woman should be like water, man should be like steel. Okay, just like solid, like fluid. Okay, so but it's hard to tell whether it's solid or fluid because it's hard or soft. Okay, and so maybe this one is just a description, but still it's hard to tell the difference. And maybe in molecular levels, it will be easier to differentiate the solid and the fluid. For high school, we know that there are three most common phases of matter. Yeah, sure, definitely there are other phases of matter, right? But here we just only just talk about the three most common phases: one, solid, liquid, and gas. Liquid and gas both are fluids. Okay, so just like here, we also should know some substances can act as solids and fluids. Okay, so one very interesting. Do you think cat? Do you know the cat? Do you know cat solid or fluid? Cat. Do you think cat and the animal cat should belong to solid or fluid? Just according to your own experience. Cat. Can anyone tell me? Solid. Yeah. Most of you, yeah, even myself. Okay, I think cat should be solid. But actually, there are scientists. They have very strict. Demonstration that cat actually sometimes behave like a solid, sometimes behave like fluid. If you are interested in this one, you can check by yourself online. You can check you can Google it. Okay, cat is solid or fluid. you will see what happened there. Okay, you can see the experiments, you can see what the scientists say. Okay, it's very interesting, very fun. Okay, and actually here from the figure it shows the molecular of the solid, liquid, gas. You see for the solids, the molecules in a solid are stuck together. They stick to each other. They have very strong molecular forces, attraction forces. Sure, the attraction also composite forces. Okay, but solid they are stuck together. But for the liquid, they just have some freedom. Okay, for the liquid, for the molecules, they still just have some the molecular forces still are there, but the molecular liquid molecular just have some free to move around. For the gases, the molecules are everywhere. They have for the molecules, if there's a little molecular forces between them, they are free to move here and there. They are free to move past each other. You see, the distance between the molecules are quite different. Solid, stick, liquid, some freedom, gas, full freedom. Okay, that's like when you are little, your mom are very strict. Okay, you got no freedom, and when you become a teenager, and you have some freedom. Okay, and when you just grow up, and yeah, still I think we still have some restrictions. We can't just behave like guys. Okay, so because of the different structure of molecules. So for the solid, liquid, gas, they behave differently. For the solid, they have the shape, they have the fixed shape, they have fixed volume, right? They can't just be easily change the shape. That's why we say the solid can't deform. No, definitely for ceramic mechanics, we just study solid with no deformation. That's called rigid body. And for you also study the material mechanics, right? That's the solid with little deformation, right? With deformation, but the deformation is small enough. Okay, they can just still can keep the shape. Okay, so that's for solid. Solid always have fixed volume, and for the liquid, why? Because the molecules stuck to each other. For the liquid, they have some freedom, and so they just can't run away to other places. So they have fixed volume, but because they still have some freedom, so they have they can deform. They will follow the shape of the container. Just that's why we say if there is no glass to hold the water will spill away, right? That's for fluid, for example, like water, but the volume of the water will be fixed. But for the gas, the molecules will have no restrictions. They can be here and there by them as they wish. So no matter what kind of the container is, the gas will be full of the container, so they will have the same shape of the container. And they also have the same volume of the container. Even the container can be large, the container can be small, and the gas, well, just like the gas can do magics about themselves. So for liquid and gas, because the molecules, they have some distance, we sometimes we say if you have if your hands are small enough, you could push one molecule of a fluid one way, and another molecule the other way. What's this? This is Newton's second law, right? Okay, and they often go in the direction you push them, but for the solid you can't because they stick to each other. So for the solid liquid gas, because of the molecular behavior and intermolecular attraction forces for solid, they are strong, and the positions of molecules are fixed. So that's why they have fixed volume and definitely fixed shape. For the liquid and the attraction forces between molecules are medium, the positions are relative. They still have, they can move, but not as they wish. So they don't have fixed shape. And so for gas, the attraction forces are quite weak. They don't have definite volume, definite shape. Just, okay, say this. Okay, because the molecule behavior, they will decide a lot of properties of fluids, okay? So you can check online by yourself what is the difference between gases and vapors from a technical point of view. What are the fourth and fifth phases of matter? We just talked about solid, liquid, gas, but there are fourth and fifth phases, okay? You can do a research on them by yourself. You can Google them and you can find out the answers. Okay, because the molecular behavior, we have a very important boundary condition for fluid. As a fluid flows near a solid surface, it sticks to the surface. Because why? Because the attraction force of the solid molecule will be much larger than the liquid molecule and the gas molecule. So the gas or liquid molecule will stick to the solid surface. So it will result in the fluid will have the same velocity of the solid surface, or we say the fluid matches the velocity of the surface. We call this no slip boundary condition for the fluids. This no slip boundary condition is a very important one that must be satisfied in any analysis of fluid flow phenomena. So this no slip boundary condition, resulting at a solid boundary, the fluid will have zero velocity relative to the boundary. Okay, this is called no slip boundary condition because of the attraction forces of the molecules. The solid molecule have strong attractive force, and liquid, gas, when they pass on the solid surface, they will stick to the solid surface. Okay, so here, let's say we have a fixed plate and we have a plate moving with a uniform velocity u. Tell us the velocity of the fluid contact with the lower plate, contact with the fixed plate, the velocity should be equal to what? This is a fixed plate, and this plate is moving with a uniform speed, u. Just now, we know that when fluids pass through the solid boundary, they will match the velocity of the solid boundary, or they will have the same velocity with the solid. So just like here, water or the air, they will have the same velocity of the plate. So because there is no relative motion between fluid and boundary, so for the lower plate, for the fluid in contact with no plate is stationary, the velocity should equal to 0, right? That's why here the velocity is equal to 0, okay? And for fluid in contact with upper plate, again, the fluid will match the velocity of the moving plate. And so the fluid in contact with upper plate will move also at speed u. This is a definition of the no-slip boundary condition. This no-slip boundary condition is really, really, very important. Okay, you need to always remind yourself. Okay, so this is a reflection of the molecular behavior of the solid, liquid, and gas. And we can just see the movie. I know what's wrong with it. Okay. It will not happen. Okay. This time. Okay. Oh, I know what's wrong. Okay. See. I know what's wrong. I can play it later on. This. I know it. Okay. I will show you next time, okay? Here it states as the fluid flows near a solid surface, it sticks to the surface. That means the fluid matches the velocity of the surface, the so-called no slip, okay? Condition is a very important one that must be satisfied here. Dye injected at the bottom of a channel through which water is flowing forms a stagnant layer. That means the fluid, they are stagnant, that they don't move near the bottom. Due to the no-slip condition, as the dye filament is moved away from the bottom, the motion of the water is clearly apparent. Okay, so there will be a significant velocity gradient is created near the bottom. Later on, this is boundary layer, we will know. Okay, so we just try to tell which one belongs to solid, which one belongs to fluid in terms of the molecular behavior. But we can't look into the molecularness of the body, right? So we want something more about the definition, about the differentiation between solid and fluid. And so we will say it. Okay. Here again, still the experiments. Okay, this experiments by Newton, very famous. Okay, consider again a material between two parallel plates. Okay, again the bottom plate is fixed, but the upper one is free to move with uniform speed. Okay, if it's a solid, I mean, just between the two plates. If it's a solid body, just like steel or just other materials, we know the top plate would be displaced through some small distances. It will have a small deformation, right? Or just here, according to what you have learned in material mechanics, you will know that there will be shear force. There will be shear force developed on the surface, upper surface, to resist the applied force P. Okay, this tau, the shear stress times area, will equal to the pulling force P. Okay, so we know if it's a steel, and we know that the steel will resist the shear by static deformation. Okay, and we have, I think we have this very famous shear strain and shear force, like this one, right? Do you remember this one? This graph in material mechanics for just still when it's under the action of the pulling, what will happen to the string, right? For this one, can you memorize this? I always tell students to memorize this, just like for the psychological. You can explain this. This one actually is exactly what happened to you when you're under some pressure. Okay, when the pressure increase and you feel bad, right? You feel bad, and the anxiety increase with the outside pressure. I mean, psychologically, okay? And then the pressure increase, and then you think, oh, nothing worse, and just like this, okay? You just take it. And so your anxiety just oscillates, but that's not increase anymore. But if 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 just you are so unlucky that the pressure just increase again, pressure still increase, and then the anxiety will increase also, and at some point you just fall apart. It's class. Okay, so I always just tell students to memorize the curve in material mechanics in this way. It will be easier to memorize no matter when you are senior, you still can draw this just like me. I forgot. I just studied material mechanics 30 years ago, but still today I still can draw this. Okay, I don't use material mechanics, but I still can draw this because I know this is what happened to people when they under the pressure from the life. What happened to you? Okay. So anyhow, we know that for the solids, they can resist shear by static deformation. They still have the shape, okay? Sure. And we have this famous equation. The shear stress is equal to the shear modulus times the strain, okay? So this is what you have learned in material mechanics. But what will happen to fluid? What will happen to water if it is a solid between two parallel plates, which is subject to still the lower plate is fixed, the upper plate is moving with speed u, and we pull with the upper plate with pulling force P, we know it will start to move, right? And similarly, there will be shear force act on the plate. The shear force act on the plate, but the fluid will just can resist shear by a fixed deformation. No way, no. If there is a shear force, the water will keep deforming. Okay, it can't resist. Sorry. Again, I don't think it can. I don't think I can show you this movie. Okay, let's see whether we can show this. But anyhow, I will show you. Sorry. I will show you Thursday. Okay. Okay, so here for the fluid, it can't resist the shear force with a fixed deformation. We know that. Now, only we know that on the condition the plate is moving, the water will move also. Okay, so what is a fluid? In point view, fluid undergoes continuous deformation under the action of a shear force. Or we can say, if there is any shear stress applied to a fluid, no matter how small the shear stress is, it will result in motion of that fluid. Or maybe you can think like this way. If you try to pour a solid, like try to pour a wood box from this glass to not another glass, the box, it will still have the same shape, right? Same volume. But if you try to pour the water to another glass, the water will change its shape. The water will deform, right? The water will experience deformation. And if you pour it, the water will continue deforming. Or if we say, if there is no glass, you just spill the water onto the ground. The water will keep flowing on the ground. Okay, so that's what we see the difference between the fluid and the solid. The fluid moves and deforms continuously as long as the shear is applied. Just like here, or the movie I will show you on Thursday. The fluid can't resist. Here, this is the shear force, okay? We know this, right? The shear force or the shear stress, okay, is equal to the shear force or is equal divided by the area, okay? The shear stress, no matter how small it is, the fluid will continue deform, okay? So this is the deflation. So when you talk about fluid, you should know the difference between solid and fluid is whether the body can resist with the shear force with a fixed deformation or not. Okay. So later on, we also, because of deformation, we will say for different fluids, that some deformation is easy, some deformation is difficult. Just like if you pour a water to another glass, you can do that within 1 second. But if you just pour silicone to another glass water, it's very difficult. So later on, we will introduce a very, very important quantity to describe the difficulties or easiness of the deformation of fluid. Okay, that's viscosity. That's what we will talk about on Thursday. And also, it's very important that we know that for fluid mechanics or for hydraulics, for thermometric mechanics, for material mechanics, we have a very, very important assumption, continuum assumption. They study continuum flow. Just now we saw the molecules for the solid mechanics. The molecules, they stick each other, but they still are not continuous, right? For the fluids, for the liquids, just like water, for the gas, just like air, the molecules, they just part with each other, and they even for the gas, they don't have the fixed position. So at the microscopic scale, the fluids are composed of molecules distant from each other. That means they are not continuous. But we need to ask ourselves the questions. Is it possible to keep track of all these molecules? Just like here, For the air, only 1 meter cubic, okay, it's about 10 to the power of 25 molecules just within a box, a small box for of air. For a glass of water, it still is 10 to the power of 25 molecules. It is impossible for us to keep track of all these molecules. We don't look into molecules. We can't find them by themselves. Okay. We can't keep track of all the molecules. And do we need to keep track of all these molecules? It's necessary? No, for us, for civil engineers, actually for most engineering problems, it's not necessary for us to track molecule one by one. And actually, we prefer to study engineer problems at the macroscopic scale. That means we don't treat fluid as not continuous. We don't study molecules. We treat fluids as continuum. And we don't concern with the behavior of individual molecules. We assume the fluid behaves as a continuum. What does it mean? We just only interest a point which we sometimes we call fluid particles or fluid elements. They are full of thousands of molecules. Okay, that means within the smallest region of interest, or we mean within a point, there are this number of molecules, there are thousands of molecules, and so like this way, the fluid populations, they are function of points. What does that mean? Just like this is molecule for the water, right? And they are not continuous. Okay, they are not continuous. But we instead of study the behavior of individual molecules, we don't track one by one. We just study this small region. We study this point. And within this region, there are thousands of molecules. And by this way, the fluid properties just like density, velocity, they just a function of the points, okay, space points. Okay, that means they are single valued at a point. Okay, so what does this mean? Just for example here, this is the wind pass through the car, and we just here we say the speed at point A is 60 kilometers per hour. What does it mean? Actually, if you look into the point in point A in this smallest region, there are thousands of molecules, and these molecules, they have different velocity, different we know velocity is a vector. They have the magnitude, they have the direction. The molecules, they are here and there, and actually the 60 kilometer per hour is the average velocity, or is a velocity in macroscopic level. Okay, so we can see the point A had the speed at point A, the magnitude is 60 kilometer per hour, and the velocity direction is this way. Okay, so this with this assumption, we take the fluid as continuum. It's very, very important. That's why we always say in reality, in real, the word is not continuous word. The word is not continuous because it's made of molecules. The molecules always have distance with each other. They are not continuous. But we regard the word as continuum. We assume the word is continuous. Why? Because it's easier to do the analysis, and also most time we don't need to study the phenomenon in microscopic level. Okay, so with the continuum assumption, the fluid and the flow properties, just like density, velocity, pressure, temperature, they are all very continuous throughout the fluid. And also, it's very important with this assumption, with a continuum assumption, the smallest element of fluid is not a fluid molecule. But whether a fluid particle, or later on we call fluid element. The fluid particle contains enough number of molecules to make meaningful statistic averages. Or we say that, just like for example, we will have this curve, just like this is the density, and the density just like this way for the molecular. This is the number of molecules, and the molecules small, the density will vary with the size of molecules, but later on it will like this. It will keep unchanged. So this one, the smallest region will be the fluid particle, the area. Okay, you can see some book will show you the figures this way. Okay, so repeat. We don't study fluid molecule. We study fluid particle, which contains thousands of molecules, which contains enough number of molecules to make the static average of the fluid property unchanged with the number of molecules. Okay, that's why we always say in microscopic should be large enough, in macroscopic should be small enough. Okay, so we have this very important assumption of continuum. Is this continuum a reasonable assumption? Yes, in most engineering problems they are reasonable, but sometimes they fail because they depend on the Nernst number. That means it depends on the average distance traveled by molecules between connections. They have free paths, mean free paths, right? And divided by the characteristics dimension of the flow field. And if the Nernst number is smaller than 0.01, and the continuum assumption works. Anyhow, in this course, for most courses, for all the courses you learned, okay, for civil engineer, we just the continuum assumption is valid. Okay. Sure, and sometimes the continuum assumption fail, just like at great heights from the sea level. We can't regard air to be continuous anymore because the molecular mean free path may be of the same order of magnitude at the body dimensions. Okay, so sometimes, okay, so it's very important. It's relative. Okay, so sometimes in nanoscale, the continuum assumption still work, still be valid. Okay. But sometimes in just if the dimension is length, it's in meter, but the continuum assumption failed because here the Nernst number. Okay, sure, for you don't need this. Just for you, the continuum assumption also works. Okay, that's all for today. See you Thursday. Okay.